Thank you. So, a very good morning and good afternoon and good evening from wherever you are seeing this presentation. So, myself, Kshitij Singh Rathore from the School of Physical Science, NISER, India, working under the supervision of Professor Shubhankar Vedanta, would like to present my work on the Magnon mediated spin pumping by coupled ferrimagnetic garnets. So, this is our beautiful green campus located in the state of Odisha in India. So, you are all most welcome to visit whenever you are. So this would be the outline of my talk, where I will be giving a short introduction, a brief motivation, some experimental techniques, results, and summary. So what we are mostly aware of is the electronic charge current that flows from one point to another, even resulting in the Joule heating. And to that degree of freedom, the spin was also looked into, and because of which this introduction of spintronics took place. Now, even in the spintronics, when the angular momentum transfers from one spin to another, there is the results of a Joule heating because of the scattered conduction electron in the medium. But if we choose some kind of an insulating medium, the spin wave-based spin current, which is called Magnon-based spin current, can lead us to reduced in the Joule heating and even in the long dispersion of Magnon-based spin current. So for this, the rise of magnonics took place. And to this, you can see this beautiful spin wave getting transferring the spin angular momentum from its one position to another. So to govern this dynamics of this equation, the Landau-listed Gilbert equation is the governing equation, where you can see the first term giving the precisional term and the second term giving the damping-like term, with the parameter alpha, the giving us the magnitude of damping in the Gilbert damping. Because for this coherent information processing, these spin waves are generally used because of this amplitude nature and the phase of the wave, which helps in the transfer of the information from one medium to another. So in these hybrid magnonic devices, we can also tune these coherent information processing via the coupling between the magnons phonons, magnon photons, or the magnon magnons. So basically, this all boils down to the two basic points, that is the control of the spin wave current and the coupling between the magnons. So for this, the chosen material or the medium was the ferrimagnetic insulators like TMIG and YIG because of its ultra low damping, high spin mixing conductance, low electrical conductivity, and low porosity too. As you can see here, on the application of applying the microwave frequency, in the presence of an external field, the TMIG magnetization transfers its spin polarization towards the heavy metal side, producing the charge current across the edges, which is measured using the nanovoltmeter through the VSP, which is a spin pumping voltage because of the inverse produced due to the inverse spin Hall effect. Clearly, parallelly, you can also see this plot where there is an increase in the spin pumping potential because of the increase in power, which is the significant signature of the production of the spin pumping voltage with the IEEE. Parallel to this, the other literature reported that work was of the YIG, the well-explored material in the low frequency region was giving such a rise in the spin pumping potential because of the splitting of the magnon of a one wave into two with the lattice interaction. So this would be interesting to find out if the magnon can also help us in the production of this increased spin pumping potential at some interface. So for this, we have chosen some of the experimental techniques present in our NISER for the deposition of thin films and structurally characterize them. So for this, we have chosen the two ferrimagnet as YIG and TMIG and a heavy metal as a platinum. For this, we have taken the S series of YIG and single layer, which is produced using the pulse laser deposition technique, and the single layer TMIG, and then bilayer of YIG and TMIG, where YIG is on the bottom and TMIG is on the top, and vice versa, where YIG is on the bottom and TMIG is on top. So similarly, with this parallel series of S, we have a P series parallel, which is in which we have deposited platinum as a heavy metal using the sputtering. These thin films were later then characterized using the structural characterization for the XRD, where you can see the clearly well-grown YIG and a TMIG film on the 444 oriented GGG substrate. Clearly, the absence of any additional different peaks apart from these YIG and TMIG and the substrate peaks gives us an idea of how the pure grown these thin films are. And from the cross-sectional TM images of these samples, we can characterize like the thickness of the TMIG thin films of a 30 nanometer, YIG of 100 nanometer, and the substrate that you can see here. And clearly, a good interface, sharp interface also gives us the clear idea from these cross-sectional images. And the ICED pattern also tells us the epitaxial nature of these thin films, and the calculation of the lattice constant for them, the XRD and TM also confirms the well-grown oriented these thin films with the corresponding literature. These thin films then were magnetically characterized using the flip chip based broadband FMR, where you place the sample on the flip chip CPW, and then these during the absorption of the spectra, these derivatives are plotted with this corresponding FMR signal of the P1, P2, P3, and P4 samples. These derivatives are then fitted with the Lorentzian equation, where we take zero crossing point as a H resonance and the peak to peak distance as a delta H. These are then plotted with the corresponding frequency, which are then characterized to take out the damping parameter alpha from these samples. So from this, you can clearly see that there is a certain increase in the damping value when the platinum is deposited on the thin films of the YAG, TMIG, and the YAG even in the mode of YAG, TMIG, and TMIG in the case of YAG, TMIG. So this increase in the damping value suggests us that there is a presence of some spin pumping behavior in the samples. So for this, we did the measurement for the inverse spin Hall effect, and simultaneously when the FMR was taking place, and that is shown in this red curve, the blue curve signifies the signal from the nanovoltmeter, that is a voltage signal of the corresponding samples. And clearly here, in the samples of a bilayer, YAG and TMIG has two distinguished peaks. Corresponding to them, there is a signal of corresponding to with the blue curve of the ISHG signal. These ISHG signals were when rotated with the 90-degree angle was showing the different opposite sign behavior, which clearly signifies the presence of spin pumping. This was then angle dependently characterized with the change of azimuthal angle, where you can see the at each angles we have plotted the V symmetric and asymmetric after doing the fitting with the V Lorentzian equations, having a V symmetric and asymmetric component. And in this plot, you can see that there is a significant rise in this V symmetric signal as compared to the asymmetric signal because of the component of the VSP present in the V symmetric signal. So VSP here denotes the spin pumping potential that we get from these signals. So this VSP signals corresponding to these data shows the high spin pumping present in our system, which was later confirmed with the power dependent plot of different variation of a power, which goes in increasing with the power for all the samples that we have taken. So this confirms the presence of a spin pumping in our samples and with the corresponding spin pumping voltage, which was later here seen in the case of a YAG samples, that VSP was found to be around 180 microvolt for the case of single layer YAG. But when this single layer YAG was compared with the bilayer samples, when the TMIG is in the bottom and YAG is on top, the sample, the signal value for this sample was increased up to 220 microvolt of the signal. So, and similarly, for the TMIG single layer sample, as you can see here, almost there was a zero microvolt of signal, but later on when it was placed on the top of the YAG, it was something around 1 microvolt of signal. So such an increase in the spin pumping potential signal was leading to some of the physics behind this. So we attributed this to be a interfacial exchange coupling present in our system. So this we have recently published in the applied physics letter paper with the title of Enhancement Pumping in Heterostructures of a Coupled Ferrimagnetic Garnets. Apart from this, this could be there could be the reason of this interfacial exchange coupling, or could be due to the presence of a Magnon coupling also in our system, for which we did the similar kind of study that recently Professor Axel Heffman's group has done with the ferrimagnet and a ferromagnet system, which was a YAG and permalloy, where you can see there around the 9.4 gigahertz of the frequency, the mode of YAG and is getting avoided crosses with the mode of the YAG. This avoided crossing region signifies that there is a presence of a Magnon coupling in our system. And apart from this, the broad spectrum of the hybrid mode of a 1 and a 2 at the higher frequency of out of phase YAG and a permalloy signifies this coupling could be an antiferromagnetic coupling because of the Magnon coupling. So for this, we have taken our samples of the YAG and TMIG bilayers, which are grown propitially and coherently with the RSM, confirms from the RSM and TM images for the ferromagnetic resonance spectroscopies at a different temperature. And at the 200 Kelvin, we found that our hybrid mode present in the system gives some kind of a signature of a Magnon coupling in our system, where the YIG modes of Kittel mode of YIG is getting coupled with the TMIG mode and producing this hybrid mode. On analyzing these hybrid mode in this broad frequency region, we found that around the 6.9 gigahertz of the frequency, there is a signature of an avoided crossing region present over there. And even this behavior of the hybrid delta H method, delta H shows us that damping like torque is mostly contributing towards the coherent spin pumping and resulting in the coupling strength of a 4.4 millitesla for this system. So hence, like I would like to conclude with my talk, like enhanced spin pumping voltage was observed for the YIG and TMIG when they were placed on the top of each other as compared to the reference single layer. And the Magnon coupling were shown for the two Kittel modes for the YIG and TMIG systems. These dynamic coupling would help in the preparing the hybrid magnetic device for the future applications. So I would like to thank my professor, guide supervisor Shubhanga Vedanta for his constant support and helping me out in this great project. And also my co-workers, collaborators, and funding agencies. Thank you.
Thank you very much for your very nice talk with systematic data. So this paper is now open for discussion. Do you have any questions or comments? So we can accept one short questions. If not, I'm sorry, because of the time limitation, we would like to move on to the next speaker. So thank you very much.
Thank you.